Some of you might know Ken. I'm just going to make sure I get him up as a presenter and make presenter. So there you go. You are now a presenter. Ken is a navigator, a spotter, and a ground homing specialist, all current in Central Zone. He's a retired Environment Canada meteorologist with a lot of experience. And so I asked him if he wouldn't mind doing a presentation on meteorology, because navigation and meteorology are massive chunks of the pilot curriculum. And there's a lot of pilots who are a little rusty, to say the least, in weather. And the navigation and meteorology go together for pilots, for navigators, for search coordinators, and so on. So it's my great pleasure, and I'm indeed very thankful to Ken for him stepping up to the plate tonight for part one. So without further ado, Ken, would you kick it off and tell us about all these fanciful terms in meteorology?
Certainly will, and thanks very much, Kim. Well, I'm just getting going here. The first thing you notice that you don't have a picture of me up there. That's because, as we used to say in broadcasting, I've got a face made for radio. So just taking a look around North America, and as I get my slide deck ready, you can see that the majority of the province on this particular satellite image, which is a combination of infrared and visual, shows that we're cleaning up after a pretty ugly series of storms over the last week or so. Still a little bit of convection hanging down in the southeast Kootenays, a lot of low cloud from all the moisture that fell up in the Peace in northeastern BC, and yet another frontal wave coming in west of Haida Gwaii. So all in all, kind of a typical day for late spring, early summer. So let's get into it. As Kim mentioned, this is a topic of great interest, I hope, for pilots and navigators. And one of the things that always inspires me about British Columbia, I've spent a good part of my career essentially doing nook and cranny forecasting for this great part of the world. I love being in the mountains, and I love just the complexity of the weather. So you take a typical, say, frontal model, and moving onto the BC coast, and all sorts of weird and wonderful things happen that screw up your basic theory. All that said, though, the basic theory still does help you to do the navigation. So, as I mentioned to Kim, as a disclaimer, I'm a meteorologist, I'm not a pilot. So when I look at something like an Antonov taking off, the back of my mind, all I'm saying to myself is, it can't fly. So here to the magic. All right, last week, Pat led a pretty good discussion on CRM, crew resource management, and I asked myself the question, how does weather fit into a CRM type framework? So to illustrate that, I borrowed this slide from Transportation Safety Bureau, and although its content I think is dedicated towards commercial aviation, basically shows that we have a safe operating envelope. We're in the middle of that. And then you've got pressures from various sources that impinge on safety, workload, economic success, and the like. And in this particular context, commercial aviation, weather is viewed as basically a pressure on how well you perform economically. But I see it more that throughout my career, I've basically been focused on providing good weather information to educated users so that they can improve their own decision making. So in this case, improving pilot decision making will increase that safety margin, which is what we all want. So the content of the talk is a review of basic MET that every pilot probably knew or thought they knew, or you would have all encountered it during your ground school, and then perhaps it's drifted away with time. I know a lot of you do refresh your training, and that's great. I do hear a couple of voices in the background, so if you can mute your mic, I would appreciate that. I'm easily distracted. So we all know on some days that it's possible to, with the right equipment and conditions, go almost anywhere. And other days, we know it's best basically just to sit on the ground and wait it out. So in between, there's all sorts of variety of flyable and non-flyable weather. And a spoiler alert for later on in the talk, IFR isn't the only thing to worry about. So we get into the basics of basic meteorology. And if you're going to take away anything from this particular talk, Remember that warm air rises. When it does, the buoyancy is counteracted by gravity. That creates some sort of a pressure imbalance that in turn generates the wind. There you go. There's meteorology. Good night. Thanks. Okay. Taking the big picture, we always do that at the start of a mission. We know that the Earth orbits around the sun, that the Earth's axis is tilted relative to that orbit. The sun warms the Earth, and the result is we get seasons. And just as an aside, we're coming up on the longest day of the year this weekend, Father's Day. Although it'll actually start, I think, at 2:44 Pacific time on Saturday. Okay, so we know that with the Earth is in its planetary orbit and we've got the seasons, but then you add the fact that the Earth rotates on its own axis, and that creates this marvelous global circulation of vertical and compensating horizontal air currents. And that's illustrated in two graphics. The one on the right basically shows the trades, the prevailing westerlies, the descending air masses. You flip that and look at it in cross section, and you've got rising air at the equator, sinking in the subtropics, rising again in the mid latitudes, sinking near the poles. And we know that we have this station or frontal boundary, the polar front that we call it, that varies roughly between about 40 and 60 degrees north latitude. It's marked by the zone of strong westerly winds aloft, the so-called jet stream. And the other key concept, remembering that that bit about ascending motion. So any place where the air is ascending, you have a compensating low pressure area at the ground. Similarly, where air is descending, you have higher pressure. Simple concepts. So within the westerly flow, we have basically semi-permanent, quasi-stationary, nice big words. They're there most of the time. There's about 5 to 7 of them around the world. The two main ones being the Pacific and the Atlantic long waves. They're situated over the oceans. They exist because the oceans have such great heat capacity, and you combine that with a rotating Earth, and that's how a wave pattern starts. Then we have landform induced ones, so down lee of the North American Cordillera, lee of the Alps and Urals, and lee of the Himalaya. And those are, as I say, those are semi-permanent features. When it's a low amplitude flow from wave to trough to wave, we call that zonal. When it's high amplitude, it's meridional, and it's the meridional patterns that are the weather producers. In our part of the world, the main weather producer is out over the northern Gulf of Alaska, where the Aleutian Low sits, more or less. So you got the long waves, and then you've got shorter waves that propagate through those long waves. And they move at a much faster rate. So typical storm track in the wintertime might be moving at 80 knots. During the summertime, maybe 30 to 50 knots. And the key concept to remember here is that ahead of what we call a shortwave trough, you get atmospheric lift. And that's depicted in this graphic. You've got the red dashed line showing the longer wave pattern, and then the blue dashed line showing the short waves. And then behind a shortwave trough, you have the compensating shortwave ridge. There the air is descending and it's generally clearer. So taking that basic concept one step further, remembering that air ascends around a low, descends around a high, and we get to...
Ken, I need you back. You need to unmute your microphone. Ken? Thank you.
Yeah, I'm not doing anything. It's the system doing it.
No, I had to step in there. I can see that there's people, there's background going on, so I had to mute everybody. And
yeah. Okay, thanks for that.
Sorry for the interruption.
Yeah, no worries. So in the basic pattern that we all learn, apparently you learn this in grade 6 now, but I didn't back in the day. Cyclonic, that is to say anti-clockwise, and I know a lot of people don't have clocks like that anymore, but basically rotating in a circle in a right to left fashion around a low, and as air flows into the low down near the ground, it's impeded by surface friction, and there's the common pattern that a surface low or trough draws air in, and then it goes up kind of like a chimney, And then in the idealized case where the air is descending, it comes to the high, and then the Coriolis force spreads it out to the right, and friction slows that down as well. And that's the basis for when you look at any number of analysis charts. Typically, we cut the atmosphere up into layers, 1,000, 850, 700, 500, and so on. And we label lows and highs and troughs and the like, and that's what you see on your day-to-day pilot package sometimes. Being scientist types, we like to classify things in order to study them. And so in the case of the atmosphere, we have that semi-permanent polar front sitting somewhere between 40 and 60 north. And then we classify air masses, and we do that so that we can basically track the motion, and because the boundaries between these sort of homogeneous spaces are where the weather occurs. So south of the polar front, it's all maritime tropical type air with a kind of like a continental version of that sitting over the high desert of southwestern North America. North of that, we've got primarily maritime air with a continental component, mostly during the winter time. And then sitting up over the polar regions, we've got the continental Arctic air. So in brief, we discuss the air masses based on, are they dry or moist, or are they continental or maritime, or are they warm or cold? And the main weather maker, as I discussed for us, comes out of the Aleutian area, and so that's the so-called maritime polar. Canada has a subspecies called maritime Arctic. The basic takeaway message there is that anything off the North Pacific is inherently cool, moist, and unstable, and the instability plays a major factor in summer weather. I'm sure that somewhere back in your memory you've seen this frontal wave evolution model, this so-called Norwegian cyclone model. And so you think back, a short wave is moving along in the westerlies. It induces an area of lift, which in turn induces an area of surface low pressure. That's on the left-hand side here. Induces a little kink in the frontal boundary. The low deepens, closes, frontal wave forms as a result. It goes a little further, it goes through what we call an occlusion phase, and finally a dissipating phase. And that takes between 3 days and a week or so to evolve. During the winter, we'll see that happen virtually every 24 to 36 hours if you live on the outer coast. And during the summertime, well, we're just coming through a season where we get about one of these a week, and very soon we won't see another one until September or October. So the simple model of precipitation around a schematic frontal wave, you basically have the warm front leading the situation, broad area of generally stable air, moist layer cloud, continuous precipitation, wrapping back on the poleward side of the surface low to a narrower band of more convective, unstable type air mass, the thunderstorms and the like. Taking another look at fronts, I'm sure you've seen the textbook example that if you have warm air overrunning cold air, we call that a warm front, and you get the classical structure of cloud lowering from right to left, precipitation starting in the thicker nimbus layers. And the other pattern, if you have cold air undercutting warm, we call that a cold front, and that's that typical narrower band of unstable cloud. Generalized cloud atlas illustrates this quite well. Again, being science geek types, we classify the atmosphere. So the troposphere is broken up into roughly 3 layers, not surprisingly called the low, middle, and high cloud layers. High clouds are primarily ice crystal in nature. The mid clouds tend to be the ones that produce the precipitation, and then the lower clouds are subject to boundary layer forces. So if we think about the classic warm front there with the lowering cloud, first of all, you get this big stream of kind of milky cirrostratus cloud, the classic halo around the sun and the moon, thickens down into altostratus, nimbostratus, and the precipitation, and then scud forming in the precipitation itself. And then on the cold frontal side, the deep convection, in this case, a thunderstorm with the classic downstream anvil. And then in between, if we call that the fair weather, we've got kind of the wispy cirrus, And then down in the boundary layer, just surface heating, cumulus, or a little bit of wind over a ridge, and stratocumulus. Two early signs for a potential frontal wave, and certainly in the summertime for instability, is to watch for these pebbly-like cirrus clouds. They're called cirrocumulus. And they basically are showing the early signs of upper level instability. Later on, you'll see layers of altocumulus, bigger puffy stuff, and again, early warning signs. Looking more locally and outside of any front or just general air mass stuff, anybody that lives on the coast is familiar with the sea breeze, but certainly anybody that lives near the lakes in the interior also experiences that. So the land warms up during the day, the marine layer or lake layer moves in to replace it. You get this shallow frontal boundary, you get kind of a nice cooling breeze near to the ocean, near the water. With enough lift during the afternoon, you get some cumulus that forms, typically fair weather, but you might get a small towering cumulus baby thunderstorm. Sun goes down, cloud dissipates, the flow reverses, and you get a flow out towards the land. And then the generalized pattern of uneven ground. So take an isolated ridge or a mountain and then move the sun across it from east to west, and basically the uneven heating causes rising air currents. They converge at the top of the terrain, so you get some shallow Q that forms. Take away the sun, the clouds dissipate, the peaks and ridges cool off. They lose their radiation faster than the surrounding air, and you get kind of this breezy little downflow gust. And there's nice names that come from the European literature: anabatic for the upslope and katabatic for the downslope. All of these are generally gentle breezes, except for if they're constrained by topography. So in the case of a sea breeze, the middle of the afternoon on a coastal inlet, it may actually howl in like 20, 30 knots. And similarly, a katabatic flow, if it's off of a glacier system and goes down a tight valley, it could also be quite gusty. If you happen to be camping in the mountains, that's actually a great place to be because the bugs are away. Okay, and then the animal that most people fear, and rightly so, is the summer thunderstorm. As the headline says, just best to avoid. Again, classifying, we tend to look at them in two flavors. The air mass type, fancy term, diurnal, just means that it forms during the day and dissipates at night. And these are most common as the sun warms up the interior plateau and the eastern slopes of the Rockies. So like today was a good example. You could find clusters of them sitting over the Chilcotin, so east of the Coast Range, west of the Fraser. And then again, another favorite spot is the east slopes of the Rockies. And then frontal systems such as we had last week, well, they can occur day or night because there's an external mechanism that's creating the main cloud deck itself, so they can persist for a longer time. They're embedded, so you can't see them, so it's harder to visually avoid them. And anyway, so best to avoid fronts. The aviation hazards are all well known. Lightning, arguably not as serious a hazard as others, although I can recall flying in a DC-3 up on the Arctic coast where the lightning hit the wing just outside my window, and that certainly woke me up. So the main hazard aviation-wise is more the jolt factor when lightning strikes the aircraft. There are cases where it'll fry a compass or the like, and I'm told that some particular FADEC setups also suffer some problems with lightning, but mostly it's like you might get a hole in the skin or something like that. But elsewhere in the thunderstorm, lots of danger, a lot of wind shear with the air flow in and out of the storm itself and the associated turbulence with that. Hail, not just within the thunderstorm itself, but as much as 20, 30 miles downwind. So when you think of that anvil, if you see the anvil and you know that that storm is a hail producer, think that it may be tossed your way. You can imagine mostly in BC, we don't get the big softball, tennis ball stuff like they experienced in Calgary last week or earlier this week. But we do get a lot of the sort of toony, loony, walnut type size stuff, and that can certainly shatter a windshield if you hit a strong enough shaft. So again, best to avoid. Icing's in the list of hazards, always severe, clear icing, but as long as we're flying VFR, we're not in precipitation. There will be cases though, so early spring and late autumn where you'll get these sort of shallow thunderstorms, especially on the outer coast, and the precipitation will be a mixture of rain and snow, and that could in fact produce some icing. The main hazard for the interior part of the province, and certainly on the coast, is the heavy precipitation associated with a thunderstorm causes drastic reductions in ceiling and vis and obscures the terrain. And then the microburst. This got a lot of attention in the 80s and 90s. It was determined to be a factor in the crash of several heavy commercial aircraft. So imagine your typical summer's day, stinking hot, drier than a popcorn fart, and you see this sort of trail of wispy stuff coming out of the bottom of a towering queue, and then it evaporates below the clouds. Well, that evaporative cooling of that so-called that virga creates a density current, which then fires down to the surface at 30, 50 knots. And as this graphic illustrates, you can imagine if this microburst were to affect you just as you're on the glide slope on approach, just before the threshold, you're suddenly getting increased performance and you're compensating for that. And then you pass through the downdraft and all of a sudden you've got the loss of headwind and perhaps not enough room to react. So I borrowed this particular table from the UK Met Office. It basically summarizes observed vertical velocities, updrafts and downdrafts in various stages of cumulus. And the orange arrows highlight what's known to be the case for, say, moderate to heavy convection. And it shows, for instance, that in a towering cumulus, you may have a current down on the order of 600 to 3,000 feet per minute. Obviously, there's a turbulence factor, but the question to ask yourself is, if you're underneath something like that or near something like that, and you're flying at, say, a contour search at 500 feet in complex terrain, is there any chance that you can outclimb such a beast? And I would think the chances would be stacked in favor of nature. So I've been alluding to what we're leaving in, which is late spring cold low season. Colloquially, it's known as January. And it's a time of year where sort of pools of cold air drift down from the northern Gulf of Alaska towards the continental United States. You can imagine, as far as a track, you can imagine, say, a half full barrel rolling down a cobblestone street, and that's more or less the track of these lows. It's kind of a disorganized feature when it's offshore. You can see the spiral, and then you can see that there's like spokes in the wheel. There's these sort of troughs that emanate out from them, these shortwave troughs. So each one of these troughs, as it swings around and heads in a more poleward direction, lifts up unstable blobs or pulses of moisture. Those manifest as what looks like a frontal wave, so a little bit of warm frontal type precipitation or cloud followed by heavy duty convection, and pretty long periods, a week to 10 days at a time, and then a 2 or 3 day break. This is basically the convection season for the south coast as well, and even the outer coast will experience this type of a pattern of small thunderstorms. The general hazard for us, ceilings and visibilities will be reduced within the precipitation. Any place where there's onshore or return upslope flow, you'll be getting terrain obscurations. And then, as many motorists discovered last weekend, the snow can be pretty low. I think there was something like 5 centimeters of snow on the Okanagan connector on Sunday morning. So these two pictures here, they just show a snapshot of last weekend's cold low event. The one on the left was from Friday in the evening, and it shows the kind of dog's breakfast around the upper low offshore with any number of thunderstorms and kind of like a fanning out layer going into Alberta, already getting what we call the return circulation to the north, and this is what led eventually to the heavy precipitation over the BC piece. The right-hand side shows the morning before the big storm that hit Calgary. So again, you see the moisture that's off the sort of northwestern states is moving up, thickening up as the trough kind of lifts it in that direction. Heavy convection out in front and a wraparound back, and lots of mayhem. So anyway, getting back to more conventional stuff, which as we go into summer, we expect more in the way of just fair days, afternoon winds, shallow convection. But any time of year, when you've got sufficient wind, and this particular graphic suggests 20 knots, I'd suggest anything more than 15 or so, you're going to feel the effects of the terrain as the air flows over it. So a classic place for it is to just on the lee side of a steep mountain slope, and you kind of get a little rotor that spins off, and if you happen to fly through that, you'll get a little up and down motion. Certainly the convection underneath a towering Q or a cumulus, so you're all familiar with that kind of rising current underneath the cloud base, and then the descending as you go out into the clear again. And then once we get a few clear nights, we will get the classic case of the inversion, that is where the temperature is cooler at the ground than it is immediately aloft, and that boundary layer between the mixed air and the cool stable air at the ground is an area of kind of shallow turbulent flow. Anyway, we'll take a short break there. I've been yattering on for about half an hour straight and ask if Kim has got any questions from the chat.
I'm just having a look at them, Ken, and most of the questions are regarding the microphones that were hot there. I know I've been hammering on about this for 8 weeks in a row now.
Yeah.
But I'm not seeing any specific questions in here. So if you go ahead and drop them in the chat area, or if you wish to unmute your microphone to ask Ken a question, or you can wait till the end.
Well, while we're waiting for anything like that to happen, I picked up this picture from the Environment Canada site, and this was from 5:30 local time today. We're looking at an infrared shot, and just another quick summary of what we've experienced. We've got the cold low is now sitting over western Montana. Lots of heavy convection over the Idaho Panhandle. A few clumps still moving their way down through the Purcells. Lots of high cloud, but not a lot of precipitation over Alberta. Extensive low cloud still blanketing the east slopes of the Rockies. See a nice clear area over the interior plateau. Clumps of convection. You see that clumpy nature as opposed to sort of the layer type stuff there over the Chilcotin. And then the next storm coming in over Haida Gwaii. And interestingly enough, something we haven't seen for a while because of the whole COVID clampdown. If you look carefully here off the coast, those are contrails. Some are heading towards San Francisco, it looks like. Some of them are departing out of Portland and perhaps out of SeaTac as well, all heading across the pond to Asia. And you can see the same thing up over northern Alberta, some fairly good ones. So I would imagine that those are the Tokyo to Chicago tracks, and there could be a little bit of action happening around Cold Lake, which at the air base as well. Anyway, any questions, or should we move on?
The question that was asked first, you'll address it in just a couple of minutes.
Mm-hmm.
And a question from the Northeast zone, the
Yeah.
trough and the trowel, which is, a lot of people think about them as farm implements or building supplies, but
Mm-hmm.
they are referring to meteorology. Trough and trowel, Ken.
Correct. So if you think the trough, first of all, we use the classic case, and we'll just say a trough running from. Let's go find one. Do 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 do. Right. So here's your classic case. The surface wave is here, and then this occlusion process. That's where if you were to do a cross section through about here, you wouldn't find a wave. You would simply have what looks like a trough of warmer air sitting over top of relatively cooler air. And we call that feature a trowel. The technical term is occluded front, but we've developed that term trowel. And just because it's away from the main frontal wave does not mean that it's devoid of weather. In fact, most of the heavy precipitation that occurs over northeastern British Columbia is due to these occlusions. So you can imagine this wave continuing to move up about this way, and that occlusion kind of wrapping around the low, and it kind of looks like a one-sided arrow, and basically along and within about 100 miles to the poleward side of those occlusions, you tend to get a lot of weather. And this, in fact, the cold low season will extend over the northern Rockies until about early July. I had firsthand experience with that a couple of years ago. I joined some buddies on a motorcycle trip up to Alaska, and we had, I think it was 4 degrees when we went through Liard. Yeah, hopefully that answers that question.
So the other way to look at it, trowel being the abbreviation for the trough of warm air aloft.
Correct, yeah.
Yeah. Okay, so that's it for the questions. There's a few people
Alrighty.
having microphones. We can move on to the next bit now.
Alrighty, so we're going to take in another essential concept. So remember the first 2 essential concepts: warm air rises, lows suck. The next thing to always remember, every pilot knows it because they have a meter in their dashboard. It may say altitude on it, but it's really just a barometer. It's called an altimeter. It's got a height scale attached to it. And for all practical purposes, in the part of the world that we fly in, so below about 10,000 feet above sea level, the relationship between pressure and height is close to linear. And so if you have a 1-inch change on your altimeter, that's equal to a 1,000 foot change in vertical altitude. And a little illustration of that. Again, most pilots will remember, I think they would have heard the acronym or the little ditty, high to low, look out below. It's an example. You set your altimeter, you're not actually a 707, but you've set your altimeter at a station, say it's 2996, and you fly away to another station where the pressure is lower than where you started, and you haven't reset your altimeter. So your altimeter thinks that you're at the higher altitude still. That's all it does, and you make that compensation of the 1,000 feet per inch, and you figure out based on these values what the altimeter should read. In today's world, because there's ATIS and everything else, and you've got contact with FIC, it should be an easy matter of just updating your altimeter setting before you arrival at your next port of call. But thinking about altimeters are calibrated, and they're calibrated to something called the ICAO standard atmosphere, also known as the International Standard Atmosphere. And that makes some broad assumptions about how the atmosphere looks. It says that at sea level pressure is 29.92 inches or 1,013.25 hectopascals, which happen to be millibars. The mean sea level temperature is 15 degrees. The air is quote unquote dry. And the lapse rate, the rate at which the temperature decreases with altitude, is 2 degrees per 1,000 feet, although technically it's 6.5 per kilometer. Why do you care about that? Well, because the standard atmosphere is what is used to calculate aircraft performance And just give an example, say Kelowna, like this morning we were 15 degrees. Kelowna Airport is at 1,420 above sea level. We do the math there, that 1,000 per, or 1 inch per thousand or whatever, or sorry, 2 degrees per thousand. And we figure out that the standard atmosphere temperature for Kelowna should be 12. Somebody knocking on a door? Okay. I got Robert Allen. Could you mute your mic? Thank you. So on a typical summer's day, we know that we divert considerably from the standard atmosphere. So an example, Kelowna on a July afternoon will often hit 35 degrees. So that's much, much warmer than the international standard atmosphere. And you can ask yourself the question of how that might affect aircraft performance. Pilots wait for it. It's I borrowed this definition from AOPA of density altitude, and basically it's the pressure altitude, which your altimeter reads, corrected for non-standard temperature. Using the relationship that temperature, as temperature or altitude increases, air density decreases. AOPA uses the expression, it's the altitude at which the airplane feels like it's flying. The well-known effects of a quote-unquote high density altitude: reduced power, reduced thrust, and reduced lift, all of which are not really good results if you happen to be flying close to the ground. The good news is that you don't have to necessarily go to this old style diagram. I believe it's on the flight calculators, it's on ForeFlight and things like that. You take your outside air temperature on the bottom scale, plug that in against the indicated altitude, and read off on the sloping lines what the density altitude is. So METARs will include density altitude as a remark anytime that it's 200 feet or more above the aerodrome. And so I use this example here. You'll see these two numbers again, 10 degrees Celsius at 5,800 ASL, you come up with a density altitude of 6,400 feet, or basically your airplane feels like it's 600 feet higher than it actually is, and as a result, there's changes in power, thrust, and lift. The FAA provides this very dramatic illustration of the effects of a high density altitude. So on the top, you've got your Cessna 172 at sea level, 15 degrees, taking off in about 800 feet and a nice, respectable rate of climb. Then you take that same Cessna and you take it up to, I don't know, Denver, and it's 40 degrees in the afternoon. And now that same plane requires almost twice the roll to take off, and its rate of climb is dramatically reduced. When I was putting together this talk, I just browsed around on YouTube a little bit, and I'm sure you can find lots of examples yourself. This was a case in Wyoming, I believe, and the video was taken by the passenger, who thankfully survived. So they take off on this hot, dusty day from this mountain strip, and the camera just shows the trees not getting any smaller as they eventually prang into them. So you don't want that. I know we're not landing in the trees, or not intending to, but anyway, taking the density altitude hazard a little further, I did some research on the Transportation Safety Board website, and I was looking for cases in British Columbia where crashes were related to density altitude, not necessarily the main, but at least a contributing factor in the TSB's summary. And I came up with 4 of them between 1996 and 2012, all involving light general aviation aircraft flying in otherwise good VFR in the warm season. First one, sadly, involved Casera over in the Kootenays, and we'll look at that first, and then 3 incidents in the Okanagan, a total of 11 fatalities and 2 serious injuries in these 4 cases. So as I was mentioning to Kim when I was putting together the talk, I'm aware that some of you are probably intimately aware of these crashes, and perhaps you have personal knowledge. My approach is strictly meteorological here. I'm trying to illustrate the hazard of density altitude, and I'm trying very hard to not get into human factors or any of the other stuff. So the first case, early July of 1996, there was a missing aircraft in the Nelson area of the West Kootenays, and there was a Casera aircraft that took off from Nelson Strip shortly after noon local time, a Warrior looking in fact for another Warrior. They were assigned a contour search in some complex terrain east of Kootenay Lake, 1,000 feet above ground with an absolute floor of 500. After they took off, they were observed by another Casera aircraft in the area that they were flying opposite direction to the search area. The pilot, when they was queried, replied they were trying to gain altitude prior to entering search. So otherwise, they knew something about the hazard. So at 1300, the aircraft reported ops normal. At 1340, a D&D aircraft involved in the search spotted smoke, went to the site, which was at 5,800 feet above sea level on the steep slope of about a 9,500 foot mountain. Weather at the crash site was reported to be clear, an air temperature of 10 degrees, and so that 5,800 feet and 10 degrees, that as in the previous example of calculation of density altitude, we came up with 6,400 feet. So the TSB concluded in this case, uncontrolled stall, low altitude, operating at a density altitude adversely affecting aircraft rate of climb. Shortly after that sad event, Casera executive, I understand, according to the TSB report, met and revised the mountain flying criteria for a minimum power rating of 200 horsepower. And then, as we all know, the current Casera policy is a weight power ratio of less than 13.1. And so navigators or new navigators, the density altitude and that weight power ratio, that's the reason why those little boxes are on the mission form. It's not just for completeness of the form. It's because it's to highlight one of the hazards. If you think about this, the plane is flying at 1,000 feet above ground level with an absolute floor of 500, but the potential difference in indicated versus performance altitude was about 600 feet. So kind of within the narrow safety envelope. Okay, on to the next case. This is the Beaver Amphib, and it was in late August of 2003. I remember the case quite clearly because I was part of the GSAR crew that went up to secure the site. Sorry, actually, that's the next case. I don't remember as clearly as I should. So yeah, this particular aircraft, they flew from Nanaimo to Penticton. They were on their way to Calgary, and they landed shortly after noon and then departed almost 2 hours later. They refueled. An observer on the ground was commented that the rear cabin was loaded with luggage and cargo, loaded quote unquote. The planned routing, because if you recall, that was the big Okanagan Mountain fire that was going on. To avoid the wildfire boundaries, it was Penticton, Kelowna, Vernon, Revelstoke, and then over to Springbank. So Penticton at 2100, so just before they took off, it was 26 degrees. That came up with a calculated density altitude of a little over 2,400, which is about 1,300 higher than the airfield elevation. They were found at 4,800 above sea level, just to the northeast of Penticton. CFIT, I think, is the term. So crash for undetermined reasons and climb performance adversely affected by density, altitude, and possibly relatively high aircraft loading. Okay, spring of 2012. This was the storm that, or the crash that I remember. first of two that summer. So this one departed another Beaver amphib, and it departed from Pitt Meadows at around 6 o'clock local time with 4 people on board. Landed on the lake about an hour and something later. Dropped off a passenger and then departed for the return leg to Pitt Meadows. It was hot for early May anyway, 27 degrees at Peachland, and I remember we were all in t-shirts that day. So the aircraft, when he took off from the lake, he advised ATC he was intending to fly south to Peachland prior to turning inland to the west. Air traffic control radar at Kelowna doesn't detect anything below 4,000, and no target was found on radar. Observers on the ground noticed and estimated that the aircraft was turning inland at about 2,900 feet above sea level. Motorists on the highway saw the aircraft flying below them and slightly north of the highway. So just near the Big Bend, near Brenda Mines, the impacted terrain. A highways weather station close to the crash site came up with an estimated density altitude of almost 5,300 feet, so almost 1,000 feet more than what indicated altitude would have been. RCMP en route to the scene in a helicopter reported 15 knot headwinds and mechanical turbulence. And the TSB concluded combination of high weight, density, altitude, and possibly downflowing air reduced the climb performance. And that same summer, mid-August, when you definitely would expect a high density altitude. So this was a twin Comanche, left Boundary Bay around midday and arrived in Penticton about an hour and 20 later. It had full fuel and 2 passengers when it left Boundary Bay. It didn't take on any fuel, but took on 2 passengers and their luggage in Penticton less than an hour later. They had come up the Hope-Princeton route, Hope, Princeton, Summerland, Penticton. They were intending to go back that same way. They told FSS or FIC they would climb to 5,000 and then turn at Summerland. The pilot, I think this must have come from an interview with one of the survivors, an unexpectedly slow rate of climb. Again, Kelowna radar did not detect any targets below 4,000 feet or above 4,000 feet. So they passed their planned turning point and continued north up to the same drainage that the Okanagan connector comes out of. Followed the highway, and motorists on the highway saw the aircraft below them and at about the same altitude as the crash site. So Penticton at the time they took off was 32 degrees. Density altitude between the time or the hour before and the hour after varied between 33 and 3,500 above sea level. The computed density altitude at the crash site was 7,000 feet, which was about 1,400 higher than what indicated altitude would have been. So again, the TSB conclusion, high density altitude, high weight, and a number of other factors of mechanical nature all contributed to a reduced rate of climb. So I'm not sure what to come up with as far as a summary other than meteorologically, the issue here is that the air isn't as dense as you'd like it to be. It's not winter. Perhaps now it's the first couple of flights of summer and maybe give ourselves a little bit more leeway in tight terrain. So the TSB took the opportunity after that, the Comanche crash, of just reiterating the things that we've talked about already, that higher density altitude reduces the output of the engine, the prop reduces less thrust, and the wings develop less lift, all of which is not a good thing. So that's about it for what I have on this section of the talk. Just a preview. Next week, I'm going to continue and talk about access and some general interpretation of weather products from the two Nav Canada flight planning portals, the classic AWWS site and the collaborative flight planning site. And I guess I will wrap by last word to Calvin. Bring on summer.
Absolutely. Thank you very much, Ken. That was a great review. Now, a lot of people might look at that and say that it's more pilot-centric, but quite frankly, the search coordinators have the launch authority. They have the tactical control over the air and ground crews. And some of our search coordinators are pilots and some are navigators. And I know that in actual SAR cases, there's some difficulty deciding whether it's okay to launch. And so one of the best things that you can do is have a subject matter expert in meteorology do the weather briefing and be involved in the case. And fortunately, in the Kelowna area, Ken is available to do that. In the case of GFPK, everybody was mustered at the flying club in Kelowna, Kamloops, and FIC is located probably about 300-400 feet away, and they have people who can come down and do briefing. I found that in actual SAR cases like GDTK, FESN, and GFPK, the weather was pretty horrific. And I did mention this in an earlier session in navigation that the pilots were lacking some experience. Sometimes it was their first flight into the mountains. In the case of the crew that we lost in the Purcell Mountain Range looking for the pilot, that was his first flight from Boundary Bay up into the Rockies as well. So there's a lot of commonality here, but we're flying in the same weather that these guys got into trouble in the first place. So it behooves everybody, whether you're a navigator or a search coordinator or a pilot, to be on top of meteorology. And don't just assume it's someone else's problem. If you're navigating, you need to be aware of the environment that you're flying in, whether there's turbulence, icing, what's the future weather going to be, looking at alternate airports. So this is the whole idea that we're bringing in a subject matter expert to review this. So it's not just for academic credit. So I appreciate it. And there's a couple of questions in here. If you don't mind, Ken, I'll just flick up to them. Bill had said the fire haze was during this event may have been a complicating factor during the Penticton Beaver flight. That was just a comment. I'm not sure if you can comment on that, whether that was a factor or not.
Yeah, in fact, that was, I think I did mention that because of the fire, excuse me, because of the fire smoke, they chose to take that direct route up the lake instead. You know, they wanted to fly directly over Okanagan Mountain, but because that was controlled by firefighting, they had to take a little northern route. So as far as I can tell, just looking at a map, they did the usual Naramata departure, and they just couldn't climb high enough to outbeat the terrain.
Yep. And there's another one here from Dan in the Southwest. Do you know why the METAR shows a different density altitude versus my flight plain language density altitude? E.g., my current YVR METAR shows 300 feet versus plain language of 436 feet.
Well, the METAR is only going to report to the nearest 100 feet. And I believe they usually round up rather than down.
Yeah, so the difference is 136 feet. I guess that's his point. That's the reason for his question.
Right.
Dan, the difference is not going to be massive. If it's from 5,800 to 7,500, it's a massive difference. Performance-wise, that's not going to make a lot of difference from the pilot's perspective. And yeah,
Actually,
Kim,
yeah, go ahead. I do have one more thing to say about density altitude, and that is that we take off usually in the calm and cool of the morning.
Right.
And we figure out a density altitude that goes on the mission form, but we're up there for 3 or 4 hours at a stretch, and during that time things are warming up. So if you did have that, you know, like whether it's a flight calculator or ForeFlight or whatever, just look at the outside air temperature on your airplane and look at the indicated altitude, plug those two numbers in and see what it comes up with for a density altitude. You can do it on the fly.
Yeah. There's one other question from Northeast.
Can I say something?
Just a second. So there's a question from Northeast. Demarcation line. Chopper pilots talk about a lot. Fixed wing pilots don't. Important to know about this when mountain flying, when windy, say on a contour search.
So what's the question?
So Lyle, you're on board there. You're asking about the demarcation line for helicopter pilots. That was your question?
Oh, yes, yes, I've actually flown thousands of hours in the mountains in the helicopters as a passenger, as a snow surveyor, and we flew in all kinds of weather from sunny to near zero visibility conditions, just to get that snow surveys and that information into the River Forecast Center. And what I noticed was that the pilots were always quite concerned about the demarcation line, the line which is the sort of the boundary between the uprising air over the mountain peak and then the descending rotating air on the lee side. And so whenever we would fly up a valley, we would always make sure that we flew on the upwind side of the valley, to especially if we were below that demarcation line. So, but that's something that fixed wing pilots don't seem to talk much about. And in the helicopter world, that is quite an important element.
Yeah, so essentially it's the separation of the slipstream just lee of the barrier itself, and yeah, you get a rotor circulation on the lee side. I've done a lot of time as a passenger going into ski lodges and helicopters in horrendous weather as well, and I'm always fascinated by how the pilot anticipates where the lift's going to be and rides that through the wave. So.
Yeah, thank you. So I'm just showing a slide here. This was, I actually took this photo. Ken, you probably recognize it because that's your black cap with the gold lettering. It's the SAR cap. During SAR FESN, this guy was in the area of Revelstoke and he was heading up towards Rogers Pass trying to get back to Alberta. He had 100 hours of total time. If you look at the board there, that's my handwriting all over it. Ken was doing a great job being our resident meteorologist. He wasn't taking an active aircrew role and was monitoring the weather, which was changing rapidly. You can see PRESFR, the pressure falling rapidly. So very poor conditions, temperature 5, dew point 4, very high humidity, and you see the DA on there as well. So it's awesome to have a guy who's a subject matter expert sitting at a dedicated computer terminal with internet. What he did, and this was brilliant, was taking all the CCTV footage from the area. And I'm just going to show the Black Diamond route there. I don't know if you can see this with my cursor, but basically we have Revelstoke Airport here, and he was flying the MVFR route up here. And the weather was coming down rapidly. This search went for 9 days. It was considered a fairly tight search area. So to have somebody who's monitoring the weather from our point of view when we're launching aircraft, the military certainly had cormorant and a buffalo with a whole bunch of pepper spotters on there that were in there for 10, 12 hours in the day. So it's an intensive search. And to have somebody who's not only monitoring the weather and giving us a weather window of how things are going to be going, but to look at the CCTV footage, the highway cameras watching the ceiling going down, 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 it perfectly matched the forecast. The ceiling went from 10,000 to 8,000 down to 7,000. And of course, over here in, this is an MVFR Alpha, in area 6 Alpha where the tip of the arrow is, that was the crash site, which was 200 feet from the Trans-Canada Highway. So he almost made it over to Rogers Pass. So what I'm saying is, don't just talk to a pilot and say, is the weather good enough to go flying? Look further. We have a lot of subject matter experts in various areas within our organization, and we are the largest MO in the whole of Canada by a long shot. We have people that are experts in certain areas. It's awesome to leverage the capabilities of people like Ken. I know he might want to get out in an airplane and look for the target, but when someone has this expertise, our whole fleet is relying on the search coordinator to make the right call. to launch the aircraft. So yeah, we can get PIREPs from people who are further up there, but this basically ties it together beautifully. We're a little bit over an hour. I'm not currently monitoring questions, but I want to thank Ken because he's coming back next Wednesday evening to do part 2 of meteorology. So for all of you who have attended, there was, I think, 114 people on tonight. That's awesome. It is being recorded, so it'll be probably available to go back and review again probably tomorrow afternoon. And I'd encourage you to do that because there's a lot of good information in here, a lot of great cases, including one of our own air crew who fell victim to some moderate conditions in the flight in a fairly underpowered aircraft at 150 horsepower. So I do hope you found it very interesting. The other footnote that I've got on this VNC, the green dotted line, I'm just going to demarcate that here with my cursor. It says 12 nautical miles out here. The actual tower is located here next to the highway, and there's the crash site within this green circle. We're able to get the cell phone pings from the pilot and from the passenger of the airplane, both of which were fatal, unfortunately. But it just goes to show that when we use all of the existing technology, when we leverage all of the capabilities that we have within this large organization, we can make a huge contribution here. So don't think that this meteorology session was just for pilots. It was for everybody. And I thank you for your participation. And I'm just going to call it quits at this point and stop sharing my screen. If there's any other questions, now is the time to ask them. Otherwise, we'll be logging off. So,
Kim, I just got one thing, Kim. The real important part on the DA, the density altitude, that Henry brought up just a little earlier, that when you've got a DA at altitude, it affects the true airspeed. So you can have different turning radiuses for stall speeds at higher altitudes at higher DAs than you would at the same indicated airspeed at lower. So that's really important, and everybody that should be aware of that.
Yeah, no, good comment. Thank you. That someone else had something else they had to say?
Yeah, it's Warren, Kim.
Yeah.
Okay, on the density altitude thing, the full equation is very long and complicated and takes into a lot of inputs that normally aren't available in the regular frames. So what people do, like ForeFlight and Nav Canada, they simplify the equation, and they will get different. You'll see different results because of that simplification, and what they assume. Nav Canada may assume something different than ForeFlight.
And that would account for the difference in Dan's question of the 300 versus 436. That's what you're saying.
That's right. Yeah.
Yeah, that's a perfectly reasonable explanation. Yeah.
Oh, aim high.
The one that I use just for on the fly is I take a look at the at the current temperature, figure out if the temperature is going to be, say, another 5 degrees higher, and I use because it's a nice compensation for both the drop of pressure during the day and the rise of temperature is about 150 feet per degree Celsius increase, and that'll give you a good margin of safety.
Yeah, fair enough. Okay, well, I just want to thank everybody again for your participation. We have, at least I have, most of the names in here. Some of you do need to enter your TMMS numbers. And I'll say it again, and I've said this in email replies to people, when you log on, find your name, click on it. There's a little, on my screen at least, there's a little V like a chevron, and there's a drop-down menu, and you can edit. You can make your name whatever you want. In order to get Ken up on the top of the list so I could make him a presenter, he's Adam KL Aviator, but that's Ken Little from Kelowna. So if you enter that, it makes entry a lot easier. I see caller 7, I see caller 12, I don't know who they are. So on the Pepper Maps website, there's an email address where you can indicate that that was you, what's your name, your TMMS number, so we can account for you. There was 114 people on board tonight. So I just want to thank you again. Unless there's any last minute questions for Ken or myself, I want to thank you. And Wednesday of next week, we'll be doing part 2, and I hope to see you there. And otherwise, our thoughts go out to Lorna Beatty and the whole family after Rick's passing. So if you came on late, Rick Beatty passed away yesterday afternoon. He was the Deputy Zone Commander for Northwest, a navigator and a search coordinator. So thoughts go out to the family. It's tragic loss for us. It's a lot of expertise. And I know that Lynn, the Zone Commander, worked very closely with Rick, and he was a great source of comfort and a calm hand at the tiller, if you will. So his successor, Jon, has some big boots to fill, and I have no doubt that he'll fill them very well. So thank you, and I see a lot of thank yous on the chats. So thank you again, Ken, and we'll see you on Wednesday, same time, same channel, and everybody stay safe and continue washing your hands, and please mute your microphones because it's a real headache to have to keep going in and pressing the hard button to try to turn them off. I've been hammering away at this for weeks. So please mute your microphone when the session's set. But see you again. Take care. Bye for now.
All right.